We spent the last couple of videos wrapping our heads around what a one form is and what a two form is. We even showed that two forms have a nice special shape as a linear combination of kind of coordinate one forms. And so now we want to look at something a little bit more general, and that is an M form. So an M form on TPRN, so that's going to be defined as a function. And so that function has M inputs, and each input is an n-dimensional vector, and its output is a real number. And then it has to have the two following properties. So it needs to be multilinear and it needs to be alternating. So let's see what those two properties mean. Okay, so multilinear means that we can break up linear combinations that are happening in any of the entries of omega. So let's maybe try to do this as general as possible. So let's say we have omega, and then the first entry is u1 all the way up to, let's say we have the I minus first entry. Let's maybe call that A, V plus B, W. And then in the I plus first entry, let's just pick it back up with U, I plus 1, and then all the way up to UM. Because recall that omega has M entries in it because it's an M form. And then just to be careful, let's recall where each of these things come from. So all of the UJ come from TPRN, and then V and W also come from TPRN. And then finally, A and B are just real numbers. So we've got this linear combination of two vectors happening in the ith component. And multilinear says that we can break this up in the following way. So we have A, and then omega u1 up to ui minus 1, and then we have V, and then ui plus 1 all the way up to um. And then plus B omega u1 all the way up to ui minus 1 w, and then ui plus 1 all the way up to um. So see what we've done here? We've broken up this linear combination that is happening in the ith entry into a combination of the outputs of omega. Okay, great. So now what does it mean by alternating? And so alternating means that if we switch any of the two entries, we pick up a minus sign. So we can actually do this really, really carefully in the following way. So let's suppose that sigma is an element from Sm. In other words, it's a permutation on M entries. Then omega of U sigma 1 all the way up to U sigma M. So in other words, we've taken the entries into omega and we've shuffled them with this permutation. So this is going to be equal to -1 to the sine of sigma. In other words, if it is even, you get a 0 up there. If it's odd, you get a 1 up there. Is it in the alternating group or is it outside the alternating group is essentially what we're going for here, of omega u1 all the way up to um. Great. So sometimes we'll get a plus sign and sometimes we'll get a minus sign, depending on how many shuffles we've done. So let's, as an example, let's look at omega and then maybe u3, u2, u1. So notice the only thing that's happened there is we've switched u1 and u3. So that is an odd element of Sm. So we can rewrite this as negative omega u1, u2, u3. Because we've already only done one transposition, and that's of like u1 and u3. Versus if we have omega of u2, u1, u3, that's going to be the same thing as omega u1, u2, u3. Because there we have hit it with a 3 cycle. We've hit it with the 3 cycle 1, 2, 3, but that's an even element of S3. Okay, great. Now we have a handle on the definition of an M form, and now we're going to look at special types of M forms, which can be written as M products of one forms. So I'll clean up the board and then we'll do that. Okay, so we just did a deep dive into the definition of an M form, and now what we want to do is say we've got M one forms. What M form do we get if we take the wedge product of all of them? And this is kind of motivated by the product of two one forms, in that we get the determinant of some sort of matrix. So we'll define it in the following way. So we'll take one forms, omega 1 through omega m. We've got this wedge of omega 1 with omega 2 all the way up to omega m. And so that should be an m form. In other words, its inputs should be m different vectors and its output should be a number. So here we've got inputs v1 up to vm. Those are all vectors. And its output will be the determinant of this matrix, which will give you a number. And the matrix that we have here is omega 1 evaluated at v1 in the first entry, all the way up to omega m evaluated at v1 in the last entry of the first row. And then down here in the mth row, we have omega 1 evaluated at vm, all the way down to omega m evaluated at vm. So in the ith row and the jth column, we'll have like omega j evaluated at vi. So I'll let you guys think about that, but that's pretty easy to see from this structure right here. Okay, so I want to do a couple of examples. So the first example that I want to do is, let's say we've got this product of one forms, which is also a three form, and let's say it is 2 dx wedge dy wedge dz. So again, we can either think of that as a three form, or we can think about it as the product of three one forms. Maybe 2 dx is one of them, dy and dz. So what we'll do is we'll take three vectors and see what omega does to those three vectors. So let's say our first vector is v1, and let's say that's 2 minus 1, 0. Let's say our second vector is v2, and that is 1, 2, negative 1. And let's say our second vector, which we'll call v3, and that is going to be 0, 1, 2. Okay, in order to be really explicit about this, let's go ahead and spell out what's going on here. So omega 1 is 2 dx, omega 2 is dy, and omega 3 is dz. Good. And that's actually pretty nice because we know exactly what those do to vectors. They just pull out the components, if we recall how the one forms were defined before. Okay, good. So that means in this first entry up here, we get omega 1 acting on v1. So in other words, we'll get 4 because we have 2 times this 2 right here. So for this entry right here, we'll have omega 2 acting on v1. So that's going to give us negative 1. And then finally, omega 3 acting on v1, so that'll give us 0. Okay, great. Now for this entry in the second row, we'll have omega 1 acting on v2, so that's going to give us 2. We'll have omega 2 acting on v2, so that's going to be 2. And then omega 3 acting on v2, so that'll be negative 1. And then finally, for this last row, we'll have omega 1 acting on v3, so that'll be 0, and then 1, and then 2. Great, so that's what we get for that. So let's go ahead and take the determinant here. So we'll do this by cofactor expansion. So we'll expand across the first row and the first column first. So that means we'll have 4 times the determinant of this 2 by 2. So that'll be 4 plus 1, so that'll be 5. So we have 5, and then minus, and then we'll do cofactor expansion about the first row and the second column. So that'll be like that right there. Remember that a minus sign is built in. And then we have another minus sign from this negative 1 right here. And then we have 2 times 2, which is 4 minus negative 1 times 0. So that'll just be 0. So we have that, 4. So that's going to give us 20 minus minus 4. In other words, 24. So that's what we get for this three form divided. So that's what we get for this three form, which is defined as the product of 3 one forms evaluated at these 3 vectors. Okay, so I'll clean up the board and we'll do one. For our next example, we'll take 3 slightly more general one forms and find their triple wedge product evaluated at 3 vectors. So let's look at these 3 one forms. We've got omega 1, which is dx plus 2 dy. We have omega 2, which is dz minus dx, and omega 3, which is dx plus dy plus dz. And then we've got v1, which is 2, 1, 0, v2, which is negative 1, 3, negative 2, and v3, which is 1, 0, 1. And so, like I said, our goal is to take omega 1 wedge, omega 2 wedge, omega 3, and then evaluate this at v1, v2, v3. And we're going to do that by this definition over here. Okay, great. So let's see what we get. So we're going to get the determinant of a 3 by 3 matrix. So in this first entry, we'll have omega 1 evaluated at v1. So notice that's going to give us 2 plus 2, because we have 2 in this component, and then 1 times 2 in that component, so we'll have 4. Okay, and now the next entry that we'll have is omega 2 evaluated on V1. So that's dx minus dz. So it's the first component minus the third component, so that's going to give us 2. And then finally, omega 3 evaluated at V1. So that's the sum of the 3 components, so that's going to give us 3. Okay, so that's what we have for our first row. And then for our second row, we'll have omega 1 evaluated at V2. So that's going to be negative 1 plus 6. So that's going to give us 5. And then we'll have dx minus dz evaluating on this thing. So that's going to be this component minus this component. So that's going to give us 1. Negative 1 minus negative 2 is going to be 1. And then finally, dx plus dy plus dz. But that's going to be the sum of these 3 components, which gives us 0. Now in this bottom entry, we'll have omega 1 evaluating on V3. So that's going to be the x component plus twice the y component. So that's just going to be 1. And then omega 2 acting on V3. So that's going to be the x component minus the z component. That'll give us 0. And then finally, the sum of all 3 components, that'll give us 2. Now we need to do cofactor expansion again in order to find the determinant. Let's go ahead and, in this case, do it against the last column, because that last column has a nice 0 in it. So the first one we'll do is that. And so that's going to give us 3 times the determinant of this 2 by 2. The determinant of that 2 by 2 is negative 1. Now we can skip this one because it has a 0 in it. And then we can do, lastly, the cofactor expansion about that, which leaves us this submatrix. So that'll be plus 2 times the determinant of that 2 by 2, which is going to be 4 minus 10. So that'll give us negative 6. So we've got something like that. So notice that's going to be negative 3 minus 12. So that'll be negative 15. Okay, great. So now I'll clean up the board, and then we'll look at some tricks in order to do this kind of calculation more quickly. Okay, so we've done a couple of examples of finding products of 3-1 forms. Now I want to look at some sort of algebraic method for doing this a little bit more quickly. And we're going to use the following fact, which we will not prove, but it's a fairly good exercise to prove it just using the definition of this product of 1 forms. And that is this wedge distributes over addition. That, along with the fact that this wedge product is anti-commutative, which is something we saw and proved in a previous video, makes it fairly simple in order to simplify these things algebraically. So let's go ahead and do an example where we do that exactly. So let's say we've got dx plus dy plus dz, and then we do wedge 2dx minus 3 dy, and then finally wedge dx plus 2 dz. And our goal is to simplify that. So we'll just kind of work from the left to the right, distributing as needed. So let's say we distribute this guy onto that guy onto that guy, and then dy will distribute onto these two, and then finally dx will distribute onto these two. Okay, so let's see what we get for all of those. So taking dx wedge 2 dx, that's going to give us 2 dx wedge dx. Now you guys might be saying that that's equal to 0, which is something we've seen before, because whenever you have 2 1 forms and you wedge them with each other, you necessarily get 0. But we'll just keep this in here right now. And then the next thing we'll have is minus 3 dx wedge dy. So that's what we get from this and this. And then next we have plus 2 dy wedge dx. So that's what we have from this term and this term. And then finally minus 3 dy wedge dy. Now we're ready for the dz parts. So that's going to be equal. So that's going to give us plus 2 dz wedge dx, and then minus 3 dz wedge dy. Okay, so that's what we get for the first product, which I've spelled out. And then the next thing that we want to do is wedge this into dx plus 2 dz. Okay, great. So let's go ahead and simplify this. So like we said before, anytime you have a one form and you wedge it with itself, you get 0. So dx wedge dx is 0. Similarly, dy wedge dy is 0. And then furthermore, we have anti-commutativity here, which means anytime we see something like dy wedge dx, we can put those in the so-called proper order, dx wedge dy, as long as we include a minus sign. Then the same thing here, we'll write this as dy wedge dz, and we'll change that minus to a plus just by changing the signs. And then finally here, we'll write dx wedge dz, and we'll change this minus to a plus, or plus to a minus as well. Okay, so let's see what we have when all is said and done here. We have 3 dx wedge dy minus another dx wedge dy, so that's going to be minus 4 dx wedge dy. And then notice we're going to have minus 2 dx wedge dz. So that's what we get for this one. And then plus 3 dy wedge dz. Great. And then here we are wedging this into dx plus 2 dz. So now we're going to do a similar distribution to what we did before. And so we need to take this first term and wedge it onto those two. We'll take this second term and wedge it onto those two, and also this third term and wedge it onto those two. So that's going to give us 6 terms in total. So some of those will be 0, but let's just write them all out to be thorough. So here we'll have minus 4, and then we have dx wedge dy wedge another dx. So that's what we get for the first bit. And then minus 8 dx wedge dy wedge dz. So that's what we get from this term hitting the 2dz term. And then next we're going to have minus 2 dx wedge dz wedge dx. And then minus 4 dx wedge dz wedge dz. So that's what we get from the second term in each part. And then moving on to this third term, we'll have plus 3 dy wedge dz wedge dx. So that's what we get from hitting the first term in the second bit. And then plus 6 dy wedge dz wedge dz. Okay, great. So now some of those things are necessarily 0. In fact, anytime a dx repeats itself, a dy repeats itself, or a dz repeats itself, you'll get 0. And we can easily see that over here from this definition, because that is the same thing as having 2 identical columns in this matrix with which we are taking the determinant. But anytime you have 2 identical columns, you know that you're going to get 0 as a determinant. So here we get a 0 here. And then notice all these 3 are different, so no 0 there. Here we've got 2 dx's, so that's 0. Here we have 2 dz's, so that's 0. And here we have 2 dz's, so that's also 0. So in the end, we have this non-zero term and this non-zero term. Okay, so I'll go ahead and clean up the board, bring these 2 non-zero terms up, and then we will combine them. Okay, so we worked down this triple product of 3 one forms to the following combination. So we have minus 8 dx wedge dy wedge dz plus 3 dy wedge dz wedge dx. Now what we want to do is turn these into like terms, and we'll do that by commuting this dx across the dz and the dy, which notice that's the same thing as doing column swaps over here. In fact, it's the same thing as doing 2 column swaps over here in the determinant, but each column swap gives a multiplication by -1 to the determinant. So if we're doing 2 of them, then that's the same thing as multiplying by -1 squared, which is the same thing as multiplying by 1. So in other words, we'll take this dx, move it here, we'll pick up a -1, then we'll move it over here and we'll pick up a -1. So in the end, we just pick up a positive 1. So we can rewrite this as minus 8 dx wedge dy wedge dz, and then plus 3 dx wedge dy wedge dz. So in the end, we'll get minus 5 dx wedge dy wedge dz. And so that is the combination or the triple product of these three one forms. Okay, so I'll clean up the board and then we'll look at a nice result which tells us the structure of M forms. Okay, so now I want to present this fact, which is really similar to something we proved in a previous video, but we won't prove this carefully. It's not that it's more difficult, it just gets kind of unreasonably technical. And that is that every M form on TPRN can be written in the following way. So we'll call it omega, and it's the sum over this thing which is called a multi-index. So we've got these I1s to IMs, and they are between 1 and n, and they are strictly increasing. So I1 is less than I2, which is all the way up to less than IM. And then we've got this A sub I1 up to IM, so that's just a number. And then we have dx1, wedge dx2, all the way up to wedge dxm. So notice we've got m terms there. Okay, great. And so in other words, the space of M forms is spanned by these kind of objects right here. Okay, so let's go ahead and set n equal to 4 and look at some examples. Okay, so maybe the first thing to look at is zero forms. But zero forms are really just the numbers themselves, so R. So after that, we want to look at one forms. By this observation, we can see that one forms can be written as linear combinations of elements from the following set. We've got dx1, dx2, dx3, and dx4. Great. And now what about two forms? So two forms will actually have 6 possibilities, and those are given by dx1 wedge dx2, dx1 wedge dx3, dx1 wedge dx4. So notice here we've got some increasing from the first entry to the second entry. Next we have dx2 wedge dx3. We don't need dx2 to wedge dx1. For one thing, it doesn't obey this rule up here with the multi-index. For another thing, dx2 wedge dx1 is the same thing as negative dx1 wedge dx2, so we don't need it. Then dx2 wedge dx4, and then finally dx3 wedge dx4. So that is 6-dimensional. And now let's look at 3 forms. So 3 forms are kind of dual to one form in that instead of keeping one of these, we throw out one of these. So there's the one where we throw out dx4. So we've got dx1 wedge dx2 wedge dx3. Then the next one would be maybe dx1 wedge dx2 wedge dx4. We would have dx1 wedge dx3 wedge dx4, and then plus one more. Great. And then 4 forms, there's only one of them. And 4 forms are kind of dual to 0 forms. And in this case, we've got dx1 wedge, dx2 wedge, dx3 wedge, dx4. And you might say, well, what about forms bigger than 4 forms, like 5 forms? But that's going to be impossible because the only way to get a 5 form is to repeat one of these. But if we repeat one of these, we get to 0. Okay, so hopefully we've built some intuition on M forms on TPRN. I think this is a good place to stop.